another lengthy problem, right? And it will feel lengthier because I don't use numbers. So every time I'm going to drag everything in terms of symbols, right? But of course, if you start plugging numbers, it would be shorter, right? Okay. So as I said, 2 boxes and with friction. 2 boxes on the horizontal table. So this will be number 4. So let's say 2 boxes on a table. And of course, with friction. So mass, what is given? So let me write what is given. Masses m1, m2. Coefficient of kinetic friction, because they're going to slide. We're going to slide them. And what else? Yeah, that's it. That's it. Right. And again, no numbers. So let me draw the picture. You know what? Let me draw the picture here, and then I'm going to redraw it. So this will be our table. So then there's a bigger box is first one. So let's say here 1 box, here the second box. And we're going to push it with applied force, some force Fa. Okay, it's not my final picture. It's just a picture in order to describe the situation. So a real picture for free body diagram, I'm going to sort of separate these boxes for the sake of clarity, for a better picture. Right? And what we need to find, actually, good question, acceleration, I think. Yeah, we need to find acceleration, and we need to find the force, because this box is going to exert force on that one, and that one is going to exert force on that one. And of course, they're equal in absolute value. You remember Newton's third law. So we need to find that internal force inside of the system. Right? Again, guys, don't try to see immediately the answer, how to do it, how to get there. The same procedure. Draw the picture, all the forces, coordinate system, and an equation in the x direction, equation in the y direction. Again, you can make some mistakes, but it's a life, right? So it's a learning curve. But as long as your application is sort of following the method. Right. So let me write what needs to be found. What needs to be found? So we need to find acceleration. Why I'm not writing subscript?
We just have one axis to worry about?
Yeah, because it's a common acceleration, because the system is rigidly coupled, essentially, right? So, of course, acceleration is going to be the same. And the second I cannot write because I haven't introduced forces. So let me first draw a free body diagram, and then after that I can legitimately write down what needs to be found in the second part. Okay, so now I'm going to separate boxes for the clarity, and let me draw. So this will be our table with friction. The first box, let me draw here. The second box, let me draw slightly further apart. Again, that doesn't mean that they are separated. They are connected, but for the sake of free body diagram, I drew it like this. So, in coordinate system, I think the choice is obvious, right? Y, vertical, x, horizontal. And you know what? Also, since we're not going to use kinematic equations, so the place of the origin is not that important. Right? So I'm going to just draw x and y over here somewhere in the corner. Again, if you use kinematic equations, that you need to show where is the origin, because x naught, y naught, it's important for x naught and y naught. But right now, it's not that. So my y-axis and x-axis. OK, so we have that somewhere in the corner so that it wouldn't interfere with our forces. So applied force, we push it. So yeah, what is also given this applied force? F applied. Right. Yeah, that force will be at the end. Okay, so now let's draw applied force. Here I'm going to draw it FA. Then, okay, normal force gravity in a vertical direction. I'm not even asking, right? So, the first box is M1. I need to label them. Now I realize, so it's M1. This is M2, right? So that's applied force. Now gravity M1G. And in problems like this, when there are two objects, guys, don't skip subscripts because it will create a mess, right? I can do also, but usually after a couple of steps I realize, oh my god, here there is no subscript. M1, M2. Don't skip it. So normal force up. Okay, let me draw it here. So it will be F, and I will label it N1. Yeah, F N1. Normal force acting on the first object. Right. And other forces? Pushing force is already there. What do you mean by pushing force, huh? Friction, of course, friction. The whole thing is going to be, since we're pushing that way, of course, friction. Oh, velocity will be that way. Velocity that way. So in this case, kinetic friction, opposite direction. So friction force F kinetic 1. Every time now we're adding subscripts. And anything else? First object.
You already mentioned friction. I don't see it.
You see. It's already on the whiteboard. Pretty much I told you, remember, that now let's discuss this situation.
Oh, you didn't say gravity yet, did you? No?
No, gravity is here, the first one. The object, okay, you remember actually these objects are next to each other. I separate them so that it will be easier to see which forces act on this object and which forces act on that object. I see a hand. So what else? Come on, look. This object pushes this box. So this box, of course, come on. Why are you invading my territory, pushing me here? Of course, I will push you back, right? So,
It's the normal force from.
yeah, some kind of normal force, yeah, interaction between these two boxes. Because for this box, it's some kind of surface in front, which, of course, that pair of internal forces. Essentially, it's forces within the system, our system of two boxes. So, right. Yeah. Which way I drew them? Like this. So this will be my force. You remember subscripts? First subscript, it indicates on which force, on which object that force is being exerted. So in this case, it acts on 1. So the first subscript 1. The second subscript, it's the source of that force, object 2. Right. So I will write F1, 2. Again, the first subscript is the victim who experiences the force, right? And the second is the bully who exerts the force. Okay, great. Now it's a complete set of forces for the first object. You see, now it's more complicated, right? Okay, we'll have more terms. Right. So the second, similar, right? So again, there will be gravity, M2G, normal force, Fn2. Don't even think moving this applied force and draw it over here. Because very often students think this way. This force pushes the whole system, right? So this object also moves because of that force. So let me draw that force also here. No, we model it in this way. We draw only forces directly acting on that particular object. So of course, effect of this force will be brought to this object through this internal force. So over here, I'm going to draw force F21 through that force. The influence of that force will be will affect the motion of the second object. So don't draw that Fa next to the second object. Only direct interactions, no some kind of long distance, right? So every time there are some forces, internal forces, and they will take care and move the effect of the first force into the through the rest of the train. And it's a very common mistake. It's a very common mistake because you're trying to apply your everyday logic, right? So now this force, which is we are going to call F21, will take care of the effect of that force. Right. Because of this force, this object will move. And the last force, friction, of course, friction, right? So friction on the second object. Okay, you know what? Let me draw it slightly lower because this subscript is in my way. So FK2. Whew. So now you see that Newton's second law is going to be messy. Okay, so free body diagram is finished, and now next step, let's move all this information into the Newton's second law, x and y direction. But now we're going to apply x and y equations twice, for object 1 and for object 2. I will probably start with the second one because less number of forces. Yeah, M2. Let me start with M2. Before we had every time only one object, so only two equations in the x and the y direction. Now we have two objects, x and y, and x and y. So we're going to have sort of like 4 equations. So now let me write something like this. First, M2. I will start with the end of this train because it's less number of forces. So, and two equations. So, and now I will start with the y equation, right? Because we need the normal force to find the kinetic friction force, right? So, let me do it. So, sum of the forces in the y direction equals to mass. It's 2 subscripts. You remember? Now we have 2 objects. Be careful with those subscripts. And times acceleration of the second object in the y direction. And then I'm going to do the same with the x. And you see any subscript next to the acceleration because it's a common for both objects in the x direction. So I immediately drop it. So acceleration in the y direction. 0. Again, we need to apply that fact that we observe there is no any motion in the y direction. Again, you need to be pragmatic in this case and apply observation. So, right. Okay, that's it. So now we have 2 equations. So now let's move all the information. So in the y direction, it's this object, normal force positive, weight negative. And it equals to 0. So, yeah, Fn2 minus m2g equals to 0. It's like what we did before in already couple of examples. So you see it's exactly the same. So now normal force. And even on the exam, if you write immediately the value of the normal force, I think I can buy it. So it will be normal force on the second object equals to m2g. And now we can immediately find the value of the friction force, right? Although the friction force in the horizontal direction, but its value is determined by this value, by the normal force. All right, so from here I can find that F kinetic 2 equals to mu kinetic F normal. Again, this is the experimental expression, right? So we introduced it a couple of classes ago. So, and now we can write kinetic friction, coefficient of kinetic friction, m2 times g. Okay, so let me underline it. And just a side product of application of Newton's second law in the y direction. Otherwise, it will be kind of, you found the normal force, and what's that? Okay, so now the essentially equation of motion for this particular situation. So equation in the x direction. So let me draw it like this, because on that line already I drew that. I wrote that. Whew, x-axis. F2 1 in the positive x direction. So it goes into the equation with plus. You see this F2 1. Then kinetic friction, negative x direction, and that's it. Two forces. So, all right, F2 1 minus F kinetic 2 equals to M2A. So the first equation just to find the normal friction force, and now this is the equation. You see, again, once you have in front of you free body diagram, now it becomes significantly easy. It's just difficult to make a mistake. Just move all the information. That's why I usually fight even with some upper physics major students, upper level. Draw diagrams. Right? All right. Okay, so now let's just move this information into the equation. Right. And we will get equation number 1. Right. So yeah, let me write it over here. So I will continue. So F21 minus mu k M2G equals to M2A. Equation number 1. How many unknowns do we have in this equation? Bless you, bless you. So from the mathematical point of view, we need to understand where we are. Are we in a good shape? F2 1, actually, that's my second part. You remember at the very beginning I told you it was too early for me to write what needs to be found, and then I forgot to write that. That's our unknown, right? So B, part B, we need to find these internal forces, F2 1, which is, of course, equals to F1 2, and we need to find them, right? So one unknown, mu is given, mass is given, and acceleration unknown. So we have two unknowns and one equation. So for now, it's not good. So we need to find the second equation. Of course, the second equation will come from the first box, right? Okay, so you see. So now we exhausted. So everything that we can extract from the first box is already in front of us. Now let's do M1. Right. The same, y direction, x direction. You know y direction, let me write immediately the value of the normal force. No, let me, I don't want to cheat. Of course, this is 0. Again, we apply observation, right? And, of course, from here, so Fn1 minus m1g equals to 0. So we'll get the value of the normal force again. And from here we can get the kinetic friction, right? Kinetic friction, Fk1, it will be mu k times, again, we assume that coefficient of kinetic friction the same for both boxes. They are made, we assume that they are made of the same material, which is a reasonable assumption. So times the value of the normal force. Again, this is the formula which we introduced. It's experimental expression. So it will be mu k times m1 times g. Right. So it's like almost identical to the first equation for object 2. You see, this line and that line essentially the same. So and now the most important, the second equation, of course, will be from the x direction. So sum of the forces in the x direction equals m1 times, and again I drop subscript next to the acceleration, right? Okay, so now we have more forces. Fa x, yeah, positive. Friction, negative. And this F12 also negative. 3 forces. Yeah, 3 forces. You see? This acts on this, and that. So it will be Fa positive, then minus F12 minus F kinetic 1 equals to mem1 times acceleration. So it's equation number 2. Because again, you remember this equation number 1, maybe I should have framed it. Right. But we have 2 unknowns, so we need the second equation. The second equation appears from this. And the same story, so you need to take this kinetic friction and plug it in. Essentially, after the next step, so once I plug this expression into this equation, after this we can write that physics is over. Because we will have 2 equations with 2 unknowns. The rest is just the algebra, how to solve a system of 2 equations. But of course, it's a little bit lengthy because numbers are not given, so we need to keep rewriting over and over and over again. Yeah. Okay, so let me rewrite one more time. Fa minus and F21 and F12. They're equal in absolute value. Remember, we need to apply that fact. It's a Newton's third law. Over here, you see I wrote Newton's third law. So it means that over here I can write, instead of this F21, I can write it is equal to F12. So we will have only 2 unknowns, not 3. Right? Okay. So minus F12 and minus mu k m1g equals to m1a. So equation number 2. You know what? I will just combine them together, and I will skip solving it, because now it's just a question of it's algebra. At this point, physics is over. So let me write that equation number 1 over here next to this. So it will be F12 minus mu k m2g equals to m2a. So it's equation number 1. So physics is over. Now the rest, and let me show that this is unknown, right? First unknown. And the second unknown, of course, acceleration. So 2 equations, 2 unknowns, physics is over, the rest is algebra. 2 equations plus 2 unknowns. So the rest is algebra. Okay, I will skip. Of course, in my notes I solved it, right? So you can see, but I will stop at this point. Of course, in a real problem, of course, I will give a numbers, so you can easily quickly calculate, and you wouldn't have to rewrite over and over and over again, because it's tedious. Of course, for 50 minutes exam, it will be it will be too much. Right. Okay, I will write. See my notes. For the solution, right? Again, you see, again, it can sound complicated, but once you draw a picture, write equations, and again, minor mistakes here and there are possible, but there is another example of the same force without friction. So now, I want to draw a free body diagram of another situation, because what, guys, something is?
Yeah, so if you don't know F12 and acceleration, how do you solve for those?
Hold it, no. F12 and acceleration are not given. These are our unknowns, so pretty much we need to find them, and we have 2 equations. You remember from the mathematical point of view, if you have two unknowns, you must have at least two equations to solve the system. From the mathematical point of view, every time number of equations and number of unknowns must be equal, and that's what we have. So pretty much what you, from this point you need to do, solve it for the this first equation for f(1,2). Just move this term to that side. It will be m2a plus that. And shoved it in the first equation. So now you have only one unknown acceleration. Here it's just a simple system of course, everyone who sits here, who is in this course, knows how to solve a system of two algebraic equations with two unknowns. Okay. Yeah, it's a pure mathematics and quite straightforward. Yeah. Okay, now based on in my section's previous quiz, we need to discuss more free body diagrams. So let me just quickly, what if we have three boxes, one on top of the other? And just draw a free body diagram. And then sort of like two boxes are on the cord, attached by the cord. So this I will probably skip. Right. Okay, so what is in terms of time? Almost 2 hours. Good. So let me solve just a free body diagram without solving. And then the rest of the problems will be easier. Again, my goal was just to drill you through the method. Picture, free body diagram, forces, equations, and then the rest is algebra usually. Again, because again, what I see, students just panic trying to see the answer. So, number 5. Again, 2 hours is not that long, right? So my record, I told you, during the first midterm exam review session, record was in physics 2 final exam 4.5 hours we were working, right? So, yeah. It was usually on Friday, once even on Halloween. Yeah. Yeah, this I'm planning to, it's not the major part of this exam, so I'm planning to discuss one problem at the end. Right, yeah, yeah. It's essentially how to move from between this set of quantities. Right? That's usually the easier. All right, so let's draw a free body diagram. So it will be 5, just a FBD, free body diagram of this situation. Let's say we have table, the first box, the second box, and the third box. I'm like a Russian nesting doll, but only one on top of the other. And because there will be tons of forces, again, let me, like in this case, separate boxes, physically separate them. Right. So the first box will be over here still. The second box will be slightly lower, right, large enough, and the last one will be here, and the surface. Right. So only forces. So I usually start with the last one, which experiences the less number of forces, and then you just keep revealing the truth, the whole truth, and nothing but the truth, right? Okay, which way I label it? The first one, okay, this will be the box number 1, this will be box number 2, and this will be box number 3. Okay, so the first one. Gravity, of course, right? Gravity, m3g, and the normal force from the box below. Normal force from the box below. So Fn3. Nothing else. Only 2. Then, second, okay, let me use red now. gravity, m2g, then normal force from this guy, because they interact, normal force from this guy. So let me draw it over here, and let me label it. Which way I labeled Fn? No. Okay, I know which way I labeled. The most efficient way of labeling it.
F21.
Yes. You remember that the first subscript represents the object on which force is being exerted. So in this case, the force acts on 2. Let me write it F2. And what is the source of the force? Who is the bully? In this case, object 1, of course, object 1. So F21. Yeah.
So say I'm like drawing a free body diagram for number 2. If I just like for the force of 1 acting as 2, if I just draw F1, would I get deducted for that? Would I get deductive if I just draw like F1 instead of F2?
Again, the way you label it, it's up to you. But this is more convenient because you immediately see the pair. This force is paired with the force which will be there. If you just write it, it will be too much of writing on the free body diagram. It will be like in the previous quiz, some students just keep writing tension, normal force. Again, you can do it, but it's makes the free body diagram kind of messy. Use the symbol Fn. Okay, I got it. Ft, tension, or just T. All right. So it makes diagram informative and also not overly complicated, right? We just need to learn the language, right? So to write it and represent it in the most efficient way, right? Again, if you look at the original Maxwell's equation, which Maxwell wrote at the end of the 19th century, they're really ugly, right? So, but now if you look at any book, because people introduced, his followers, disciples introduced nice symbols, right? So now they look like nice equations where there are curls, divergence, and so on. But original equation, yeah. So the force from here, and then any other forces?
Oh, the second box?
Yeah, the second box. Okay, yeah. You know what? I talked about, blabbed a lot about the most efficient way, and let me relabel this, because that's now I started looking, it's not the most efficient way. How would you label that force? Yeah, let's use the same. It's a force acts on object 3, and that force comes from object 2. 3, 2. I just didn't look at my notes, right? And now once I started moving and I realized, good. Okay, so now another force, this guy pushes on this guy, right? So if this guy exerts force on that one, F3-2, why not? Why are we discriminating? That guy also can exert force on that one because there is a direct interaction between those two. Yeah. 2-3. Now it will be F2-3. And that's the force which is usually missing in the free body diagram in the quiz number 2, which I gave in my sections like a few days ago, right? So yeah. Every time if there is interactions between objects, those are internal forces. So this pushes this way, this pushes that way. Right. So it's a red, so I will draw it over here, and it will be F on 2 from 3. So pretty much this force. And this force, it's that pair action-reaction forces, right? So this and this. And of course, the absolute value of this and absolute value of this are the same. That's what we use over here also. F12 and F21, right? Whew. And so that's it. 3. Gravity, the Earth, and because above there is an object, and below there is an object. 2 forces from each interaction. Right? On the right side there is nothing, on the left side there is nothing. Right. So now the last one, weight. Okay, I ran out of color, so let me use again red. Yeah, why not? Right, so M1G. Below there is a table, interaction, normal force, and this time I will label just Fn, because we didn't label table as an object. So let me write it as Fn. It's interaction with the table. And so, since this box exerts force on that one, of course that one must exert force on the box below. So now it will be F subscript.
F subscript 3.
Direct interactions, right? Direct interactions. So if this box, you see, exerts force, this one, F21 on the second box. It's on the second from 1. So, of course, at the same time, this box will exert force on the 1, the first box. So it will be now flip subscripts.
2, 1.
F1, 2. No, 2, 1 is here. The first subscript, it's the victim. The second one is the bully who experiences the force. So in this case, who experiences or which object experiences the force? It's a 1, the first object, and the force comes from the second. Right. So F1, 2. Every time when you have this pair of forces, this force and that force, the difference between them is subscript, and that's why it's easier to connect them. So they are sort of, you know, that these are that couple action reaction. F1, 2, F2, 1, F3, 2, F2, 3, right? F4, 5, F5, 5, 4, whatever. Yeah.
And so all of those are equal?
Inside of that pair, they're
So
equal.
1, 2, and 2, 1 are
Yeah,
equal.
yeah,
and 2,
yeah.
3 equals
So
to
F3, 2 equals to F2, 3. But, and then of course F1, 2 equals to F2, 1. But F2, 1 and F3, 2 are not equal. They're in a different conditions. You need to go through Newton's second law and find actually the values like what we did over, actually we didn't do it. Right? So, but of course from here you can get F1, 2, right? Yeah, yeah. Of course that's, that will be more complicated.
Can you explain why they're not equal?
Of course, because over here, this force F2, 3 and F3, 2, they only need to manage only this weight of that object.
Okay.
But here, these forces, they need to manage this box and plus that box. Of course, now these forces are going to be larger than those forces. Yeah, it's a pyramid, so people standing underneath will experience all that weight of all those guys, right? So of course, they will experience much larger force, value of the force. All right. Yeah, so that's it, right? So yeah, the free body diagram is over, completed, right? So now another, so it's a free body diagram 1, and now the second. We had the problem like this in the class, but just to review. So what if we have two balls connected with the cord? So let's say cord number 1 and cord ball number 1 and ball number 2. Right. So let's draw all the forces acting on these guys. So system M1 and M2, okay, 1 and 2, right? So you remember it's a basically problem about buckets which we solved in the class. Now it's something similar. Again, I usually start with the end, which just has less number of forces. So the second object, M2G, on this side there are no any objects. Over here again there are no any objects, there are no any interactions. Above there is a cord. Cord, immediately tension, pulling force away from the object along the cord. So Ft, let me call it 1, because there are two cords. So this will be cord number 1. So let me say it's a cord or rope number 1. So that's why I put a subscript 1. That's it. Object 1, nothing else, because there is only earth underneath and the cord above. So now object number 1, weight. You know what? I should have used different color. Let me use blue. All right. So M1G. Then, what else?
Tension.
Which one?
1.
Tension 1, yeah. So below that there is a chord, and of course, since the chord, every time in all our problems, chords are going to be massless. And it's a very, very common situation. Usually objects which we're trying to drag with the chords, they're much, much heavier than chords. So it's a reasonable approximation. So it will be Ft1. And in absolute value, this force and that forces are the same because chord, if the chord is massless, over here I wrote, if a chord is massless, tension is exactly the same at any point of the chord. Right. Okay, and next, the last force, above that there is a chord number 2. Of course, that chord is going to also exert some force. Maybe the whole system is accelerating, let's say maybe accelerating with up, and over here there is a hand, 1, 2, 3, 4, right, so maybe that hand is pulling the whole system up. So of course above that there will be also tension in the chord, it will be Ft2. Okay, so free body diagram is completed. And again, description, the same, introduce coordinate system, free body diagram here, and write down Newton's second law. Okay, next example, I will skip it, because I see you're getting tired. I'm also getting a little bit tired. It's basically your homework problem, I think. When you had two objects connected with the chord, one object is on the inclined plane and the second object is hanging over the pulley. Right, so again, you can look at my notes. Okay, almost done. So now the last example about tangential quantities, which is not that complicated at all, and we'll call it a day. Any other example? Any other questions? Okay, all right. So the last one. So it will be 7. Okay, I skipped one problem because I prepared 8. So there is a disk spinning, and we can make a dot on the disk. Okay, let's say we have a spinning disk. Right. And radius is given 10 meters. Well, it's almost like a merry-go-round. Okay, and let's assume at a certain, let me draw the picture. Right, so R is given. And let's say at this moment of time t, velocity is given. How do we call that velocity?
Omega.
It's angular. If I wanted to know information about omega, I would add angular velocity, right? Because it's different things. So in this case, it's a tangential velocity. It's a tangential velocity. This tangential velocity. So let's say v tangential is given at this particular moment of time. So at a certain t, v tangential, actually the right tangential, yeah, 10 meters per second. I wouldn't be able to use audio from that phone. Lots of background noise. No, I'm kidding. I usually use that because content creators. Say something, click like or
Subscribe to the channel.
yeah, exactly. Subscribe to the channel. I hate it, right? So whenever somebody say that, I want to close it immediately. All right. Okay. So and we know that this velocity changes at a certain rate. So let's say changes at the rate of 10 meters per square seconds. So this velocity changes at the rate of 10 meters per square second. Which acceleration are we talking about? Yeah, it's a tangential. You remember tangential acceleration is responsible describes how fast magnitude changes. Centripetal acceleration describes how fast direction changes. So if since I said about value of the tangential velocity changes at a certain rate, I'm obviously talking about tangential acceleration. So tangential acceleration is given, right? So certain rate and a tangential equals to also 10, but now of course meters per square seconds. All right. Okay, so let me check what else is given. So at this particular moment of time, we need to find total acceleration, value of the total acceleration, and then we will have to find actually angular acceleration, which you mentioned, and angular velocity, and then angular acceleration, and that will be the end, right? So now, part A, let's find a total. So let me complete the picture in order to see what I'm talking about. Of course, if you remember the lectures, we discussed that. So tangential acceleration, direction of that, since you brought it up. Okay, in the direction of the velocity, because velocity increases. Value increases, so it means that it's in the same direction as the tangential velocity. So tangential acceleration, let me draw it like this. So A tangential. And whenever there is a circular motion, there must be a second acceleration. I'm like a conductor trying to orchestrate here, right? So and here you are with your trombone. Okay, sorry, I'm getting tired. All right, and centripetal acceleration, of course, towards the center. Right, towards the center, a sub r. So I asked about total acceleration. It's a sum of these two. So all the time, this acceleration and this acceleration, they are perpendicular to each other because one is along tangential direction, the other one along radial direction, which are perpendicular to each other. Right, so I can complete this rectangle, right, and this will be our a tangent, total, which we want to find. Magnitude of which we want to find. It's a magnitude, you see. I think this problem is from one of the old final exams, like maybe more than 10 years ago. One instructor used something like this, so I adopted it. All right, okay. So of course, in algebra, in the vector equation, a total, of course, it's a r centripetal plus a tangential in a vector form. We want to find the magnitude, right? So how can we find the magnitude? Jason?
Wouldn't it just be their AR? Magnitude. Find the magnitude, wouldn't it be AR plus a total? Or not AR plus a tan?
Not just plus. You see, they're perpendicular. If they were in the same direction, what you said would be absolutely correct. But you see, they're perpendicular. So what can be used? So essentially, we have this. I'm sure that we should be able to find centripetal acceleration. And we need to find the magnitude of this vector. Of course, just simple, banal Pythagorean theorem. Of course, yeah. So of course, we need to just write square root of a tangential squared plus a centripetal squared. So tangential acceleration is given, centripetal. Can we find centripetal acceleration, Jason?
Yeah.
Yeah. Velocity is given, radius is given. Yeah. So a centripetal, it's a v tangential squared over r. Again, it's a centripetal acceleration. It's over here. It's given, right? So I should have framed it. So numbers are given. Let me just write immediately the answer. Actually, it's a simple 10 squared divided by 10. It's just a 10. 10 to the power of 2 divided by 10. I'll skip units. It's a 10 meters per square seconds. Okay, that's ugly meters, right? Okay, so now we can plug into the total, and of course, a total will be equal to square root of 10 meters per square second squared plus 10 meters per square second squared. Whew. So 10 times square root of 2, right? It will be 10 times square root of 2 meters per square second. Square root of 2, it's about 1.4. It will be 14, approximately 14. Right? Okay, so in terms of tangential quantities, these tangential quantities, we found almost everything, right? So now let's find the angular acceleration and angular velocity. So now let's part B. Let's find angular velocity and angular acceleration. Omega and alpha. Right. So since you mentioned omega, so how can we find omega, or can we find omega?
Well, we use, like I said, like that, V10.
Yeah. V tangential equals r times omega. Right? It's as simple as that, right? So every time angular quantities, this theta, omega, alpha, and tangential quantities are connected through the radius. Right? And of course, these formulas are also given in the formula sheet. So yeah, so it's absolutely banal. So it's a V tangential divided by r. So it's a 10 meters per second divided by 10, everywhere 10. So it's a 1 units radians per second. Of course, radians means what? Radians means nothing. Inside of radians, it's an empty unit. Inside of radians, there is nothing. Right, so it will be 1 radians per second. Angular velocity. Again, angular description and tangential description of the same rotation. And alpha, the same thing, the next level equation, right? So alpha will be equal tangential acceleration divided by r. We have both, right? Again, 10 and 10. 10 meters per squared seconds. You're struggling with this, right? It's a 2 times 10 to the power of 2. So it will be also 1, but now it's a radians per square seconds. You know what? It's the last piece. Let me write nicely square. So the end. The end of the review session.